So here we are starting Unit 12, the last unit of the year. And in these first set of notes, we're going to talk about some of the basics of energy, definitions, some simple equations we're going to use throughout the unit. Then we're going to get into this Hess's law idea. And this is going to cover pages 1 and 2. Page 2 is mostly just examples of Hess's law, where I am going to ask you to do reaction number 3 on your own. So let's get to it. The most simple thing we need to make sure to understand and define when we're talking about energy is what is the system and what is the surroundings. And the system is always whatever is being studied. In chemistry, this is generally a chemical reaction or a specific substance. And this scientist gets to decide what their system is. You could be a scientist studying a single substance, not even a substance and how it reacts, just how it melts or boils or freezes. Even just a single substance gaining and losing energy is something we could define as our system. Or in a chemical reaction, we have more than one chemical that are reacting with each other, but we can still define the reaction as a system and talk about and examine how those chemicals are exchanging energy with each other. We can set that system as whatever we want. Maybe we're dealing with multiple kind of mini reactions together inside a living organism, or the organism itself, like a frog in the rainforest. The frog could be our system. The rainforest is going to be part of its surroundings. Or you could be studying the rainforest and its interaction in the world. This can literally be anything as long as it's the focus of what's being studied. And as soon as we define the system, then the surroundings is just everything else around the system. So the air, your hand, the beaker, the table, all of that. And we can just simplify that down into system and surroundings. Now, the first law of thermodynamics is also going to be important for energy, because this is also known as the law of conservation of energy. This is a lot like the law of conservation of mass that says that mass can't be created or destroyed. The total amount mass is constant in a chemical reaction. While here, the total energy in a system added with its surroundings is going to be constant. So we can say that system plus surroundings equals a total number, and that total is never changing. The energy is just moving from place to place. And I have a little example that I want to show you of this to help you understand this idea, but we're actually going to skip over these two words, endothermic and exothermic, so that we can get an understanding of what this delta H thing is and better understand some of these energy flows with systems and surroundings before we talk about those words endothermic and exothermic. So delta H is the difference between the energy of the products and the energy of the reactants. And delta H, although it's nice and short and simple to say, is also known as enthalpy. And we're going to be talking about that a lot this unit. And enthalpy is just the energy or heat change in the system. So in the case of that chemical reaction, it's products minus reactants to find the total energy of that reaction. But no matter what we define as our system, the enthalpy of that system is the heat or energy change inside that system. We will often be calculating this as the sum of the energy of the products minus the sum of the energy of the reactants. So products minus reactants is going to get us this value. Now, let me help you understand why we have that kind of weird looking equation for it with this simple kind of demo here. You don't have to write this down anywhere, but this kind of helps you understand the next couple of words we're going to define and how they fit in with these first couple of words that I've said. So this circle here, imagine, is my system. Just a simplification of the system. Everything outside of that circle is its surroundings. Now, I can give my system and the surroundings a certain amount of energy that I'm just going to depict as dots. And here, our initial energy of our system and its surroundings are 10. 10 dots in the system, 10 dots in the surroundings, which means that we have a total of 20 dots, 20 energies total in this universe. Now, if I were to change the amount of energy, I would have to move it either from the surroundings to the system or from the system to the surroundings. And I'm going to start by moving 3 dots, 3 energies from my surroundings into my system. So now I have 3 more energies inside my system, and they are no longer present in my surroundings. I just moved them, just like I can move marbles. So my system has gained 3 energies. My surrounding has lost 3 energies. But if I add those up, my total here is 0, which means that supposedly our energy change is 0. And we can prove that by looking at our final energy state. The total number of energies left in my system, means original 10 plus these 3 is 13. And there are 7 dots remaining outside the circle in my surroundings. If I add those up, then sure enough, I have 20 total energies. All that we're saying here with this complicated sounding first law of thermodynamics is just that energy moves from place to place. It doesn't just pop in and out of existence. It has to start someplace and end someplace, which means that our total is a constant. Now, to that delta H thing, we said that that was products minus reactants earlier. That basically means final state minus initial state, if we're not looking at an actual chemical reaction with substances that we can call products and reactants. So if I write that down, final minus initial, which is kind of our products minus reactants here, then 13 minus 10 is positive 3. And notice how that matches up with the positive 3 energy change that occurred in our system. That's what we said this delta H enthalpy value was, a measurement of how much energy is changing in our system. So this is just telling us a little bit of information that we could probably reason through if I had simple dots that I could measure my energy with. But unfortunately, it gets a little more complicated than that when we're doing these calculations later on, which is why we're going to need formulas and equations to help us. But that idea is still the same. And so let's go ahead and go fill in the definitions for endothermic and exothermic before we move on to that Hess's law thing. So endothermic is a type of energy change or transfer where the system is gaining energy. Energy is entering the system. And I say it that way because entering just sounds like endo. So entering is endothermic. And if energy is going into our system, that means the system is gaining energy. That is always going to result in a positive sign on our delta H value. So just to kind of round this out here, if the system is gaining energy, of course, that means the surroundings are losing energy. And that's important to be able to reason through because this next part kind of confuses people a little bit. If you touch an endothermic chemical reaction, what do you think this is going to feel like if the system is gaining energy? What do you think you're going to feel? Hot, cold, nothing? Well, because there is energy changing, you are going to feel a temperature difference. But what might surprise you is that these reactions tend to feel colder. And the reason for that is because no matter whether you stick your hand straight into that beaker or not, you're not part of the chemical reaction we're studying. If you were, you would be in that product or reactant side of that chemical equation, but you're not. So you are always, your hand, your neurons that are sensing this temperature change, even a thermometer that we might stick into a beaker, is always going to be part of the surroundings. And if you feel your hand losing energy, like the surroundings are doing here, losing energy, that means that you're going to be feeling less heat, which means that it is going to feel colder, or that thermometer is going to read a temperature decrease because the energy is going away from the surroundings, away from you. It's going into that system, but it's being used for something. So it's getting kind of used up in that reaction, going away, so you can't feel it. Hopefully that makes sense. If not, I can kind of show you some examples so that you can understand this a little bit better. But basically all of what we just said about endothermic, the opposite is true about exothermic. In exothermic reactions, energy is exiting the system. So remember, it's all about that system. If it's exiting the system, that means the system is losing energy. And because enthalpy, that delta H, is all about what's happening to the energy of my system, that means it's going to be negative. And that means that the surroundings themselves are gaining energy. If the system is losing energy, there's only one place for it to go, And if the surroundings gain energy, and that's where your hand and body and temperature probe are, then you're going to be feeling more energy coming to your hand. More heat means it's going to feel warmer. The temperature is going to increase. So the first big idea of the energy unit is Hess's law. And this is just a way to calculate enthalpy, one of the several ways to calculate enthalpy. And Hess's law actually says that if a chemical equation can be written as a combination of multiple steps, multiple kind of sub-chemical equations, then the delta H for the overall equation is equal to the sum of the delta H's of each step. So basically, if we can know a little bit about each of those small steps that make up a reaction, we can use that to piece together the overall reaction's information. And that helps us study big, complicated reactions and understand the energy flow in them by breaking them down into smaller pieces and studying more manageable, more observable small reactions. And then we can use those to interpret and understand bigger, complicated reactions. So, overall, there's a lot of steps and information on that page about what we need to do to use Hess's law. And really, it's kind of like a puzzle. What we're going to do is find the substances in the overall reaction that you're given in one of the sub-reactions, reaction steps. And we need to make it match the overall reaction. We need to make sure we have the correct number of each substance and that it's on the correct side of the reaction. So it's kind of like hide and seek. We're trying to find our substances and get them where they need to be. And we can do some stuff to those little sub-reactions in order to turn them into that overall reaction. And we're not really focused on making the reactions into each other. It's kind of just seeing what we have to do to them, because whatever we do to those reactions in order to turn them into the overall reaction that we need, we're going to do the same thing to their delta H's of each of those little steps. Each reaction's delta H. If we flip it, we're going to flip the sign on our delta H. If we multiply it by a number, we're going to multiply our delta H by that number. We can also divide by a number, or basically multiply by a fraction. It's kind of an easy way to think of that. And if we do that, then we do the same thing to that delta H value. And in the end, after we make sure we have everything that we need, then we can add up all the delta H's that we've got. Now, you'll notice that this tells us that we can combine identical substances that are on the same side of different steps, different sub-reactions. We can also cancel identical substances that are on opposite sides of different steps. And I'll show you how this works, but really when it comes down to it, you should kind of ignore any substances that are identical things in more than one of the steps. If you notice that happening, skip it. Leave that substance for later. Even if it's in our overall reaction, we don't want to make that a priority because those can get kind of messy. Focus on everything else first. And then if everything else matches, we're going to come back and we'll check and see if these things have combined or canceled in a way that's going to give us our overall. And if not, then we'll make a change there at the end. But it's important to get everything else kind of balanced and matchy first. So let's look at this example that I have down here at the bottom of the page. We are trying to get this overall reaction here from these two little sub-steps, sub-reactions here. And the way I go about this is by looking at each substance in my overall equation and finding it in my sub-steps. So I'm just going to color code each of my substances a different color here, so I can better keep an eye on it. And if you notice, that's all of the substances that were in my overall reaction. But I do have CO2 in both reactions that is not technically in my overall. So just by kind of taking a look at what I've got, finding the important things in my reactions can kind of get me a plan of attack here. So now what I'm looking for, I'm going to go through and get what I need. I need 2 carbons on the reactant side before my arrow here. And if I'm looking at carbons, I actually see 2 carbons right here in my first reaction. The only problem is that they are after the arrow. They're on the product side. So what we have done here, you can see right below it, I've already done this, is I have flipped this reaction so that now all of my products, that's 2C plus 2O2, are on my reactant side, and that 2CO2 is on my product side. I'm going to go ahead and color code this again just so that I can visualize and see those substances that I've committed to being down here. And I'm also going to check off this 2C up here in my overall because I can see it, the correct number on the correct side down there. So I've gotten that. I'm good. Now, next thing I see is this O2 gas. And while that is the next thing in my reaction, and I tend to just work left to right, I do notice that that is in both of my reactions. So if I see the same substance, even though there's two of these and one of those, it's the exact same O2 gas, in both of my substeps, I'm actually going to skip it for a minute, leave it behind, ignore it, come back to it later. Next thing I'm going to try and get is 2 CO gas molecules on the product side after my arrow. And what do you know? Here in my second reaction, I already have 2 CO gas molecules after the arrow, just like I was looking for. So I actually just brought that second equation down and used it exactly as it was written. No changes necessary. Now that we've done that, I can actually go back and start taking a look at those O2s. And if we do that, and this is one of the reasons why I like to rewrite my equations out, is that with these two O2s that we started with over here on the reactant side, and then I have one O2 on the product side, well, since they're on opposite sides, they can cancel, but they're only going to cancel an equivalent amount. So if I only have 1 on my product side and 2 on my reactant side, then this 1 is going to be canceling out completely, but only one of these 2's is going away. So that's why we crossed out the 2. That's no longer there. So that did get me that 1 O2 that I was looking for. So I have found all of my substances, and that means that I should be able to find my delta H from these reactions the way that they are written. Now, I wasn't focused on it before, but now that I have flipped this first reaction, what I do is I flip the sign. This number stays exactly the same. I just change it from positive to negative. And because I brought that second reaction straight down without any changes, I just brought its delta H straight down with no changes. And technically, I can sit here and cancel out those pesky CO2s and notice that now that I've flipped that first reaction, they're on opposite sides and they do cancel. But the question has never been, what will the chemical reaction be when we add it up? We already have that chemical reaction to start with. So as long as you have checked off each substance and you're confident you've gotten them in the right places and you've got everything you need, especially if you ended up checking and using each of the reactions you're given, making a change to it or deciding to use it as it is like we did here, I am confident that now all I have to do is add up these numbers and that is going to give me my enthalpy of the overall reaction. And you're always going to make sure that it matches the units on each of those delta H's that you're given. So kJ is kilojoules, and that is going to be a very common unit for these enthalpies and other energy values, this unit. So looking at the results of this example problem, it definitely gets a little messy. I mean, you had basically all of that already written out for you, but hopefully what's written here and how these things kind of relate to each other makes a little bit more sense now. So let's go ahead and look at the next page of practice problems together and go through the same motions and work through these problems together. So this first one, I'm going to start looking for 2S down in my reaction, and I see an S. I don't see anything else that is similar, so I guess that's all I've gotten, and at least it's on the reactant side, but it's only one S, not two. So I'm going to go ahead and multiply that by 2 to get the 2 S's I need. Remember, we have to do the same thing to the entire reaction. Every substance in here gets multiplied by 2, and my delta H value here gets multiplied by 2. So I'm just going to cross that out briefly as I calculate what that times 2 is, making sure to keep that as a negative 594 kilojoules, of course. Now this is checked off. My next substance, 3 O2s. I see O2s here and there. So kind of like the last problem, oxygen is kind of getting in the way, so we're going to ignore that and come back to it later. And then I need 2 SO3s on the product side, and I see 2 SO3s on the reactant side. That's the only ones that I see here, so I guess that's what I'm going to have to work with. And in order to get those on the product side, I'm going to have to flip this reaction. And I'm going to rewrite it just so that I can see that written out properly. All of my products coming over here and then turning into what used to be my reactants, which are now my products. And that is perfect. I'm going to go ahead and scratch this out since we're not using this equation anymore. We have flipped it. So I've got my 2 SO3s on the product side. Now I also need to remember, if I've flipped my reaction, to flip the sign on my delta H. So now that delta H is negative 198 kilojoules. I'm done with that number. So I have my 2 S's and my 2 SO3s, and now all that's left is to focus on our 3 O2s. And hopefully now you can see how focusing on the other substances has actually gotten me, once again, exactly what I need. Because now, even though there are O2s in both of my reactions, I can see that they're now both on the reactant side. They're both before my arrow. So because they're on the same side here, they're going to be adding up. And 2 plus 1 is 3. So I have found all of my substances, and I've made some changes to each of my reactions and their delta H's. So I'm pretty confident that these will be adding up correctly. And if we add up our delta H's, we get negative 792 kilojoules. So it's kind of just a puzzle. You're trying to find each of these pieces and get them in the right places to mesh into this bigger overall reaction. So let's try one where we have more than just 2 reactions. The process is still the same though. Start with a substance, start trying to find it, and don't just stop in that first reaction. You have to check all of the reactions to make sure you're not missing, that it's in more than one place. But this one is actually perfect because it is just 1 C2H4 on the reactant side to boot. So we already have what we need there. As we go looking for our H2 hydrogen gas, see some H2O, which is close, but aha, here is our H2. That's the only place that I see it, and that is 1 H2 on the reactant side, so that's fantastic. That is also exactly what I needed. And now this next one, we're looking for our C2H6 gas, and we want that to be on the product side. But I do see it over here on the reactant side and definitely nowhere else. So we're going to go ahead and flip that reaction to get that on the product side. And then I can get rid of and kind of ignore that original reaction here. And if I flip my reaction, I also need to flip my delta H value. So now this delta H is equal to positive 1560. Just putting that positive sign there to help me make sure I don't accidentally change it or switch it back. And so technically that is all of my pieces of my reaction, but there is a whole lot of other stuff involved here. Now, we can either just add up our delta H's because I'm pretty confident in these. I found a substance in each of my reactions that has to be in that spot. I cannot change these reactions, none of the 3, without messing up one of my reactants or my products. So I'm pretty confident they have to be where they are, and I don't have to worry about any of these other things. They should cancel out if these reactions were given to me to add up to that overall reaction. You kind of could just trust your teacher or the information you're given, but scientists don't always have perfect information, perfect reactions given to them. So the process that you would normally go through as you're trying to discover these mechanisms and these sub-steps, or researching an overall reaction and looking for more overall information, is look at each of those substances that we are hoping cancel out. Here I have 2 H2O on the product side and another H2O on this product side, and then I have 3 H2Os on the reactant side of this reaction. So I have 3 total products, H2Os here, 3 total reactant H2Os there, so they do cancel out completely. Then our CO2s here, I have 2 on the product side here, 2 on the reactant side here, simple canceling. And then our O2s, I have 3.5 on the reactant side, and I have 3.5 on this product side. So after taking a little time to make sure, yes, all of those pieces do cancel out and leave me only the substances I wanted in my overall. So I can be 100% confident that I just need to add up these numbers to get my final delta H for this reaction. And as long as we are careful about our signs, final answer here comes out to 136.8 kilojoules. Hopefully this is seeming a little less scary now, and I am going to ask you to do number 3. If you're not feeling quite ready to do it right now on your own, then that's absolutely fine. Come back to it. I am going to go ahead and tell you that this answer should end up being negative 1628.2 kilojoules if you've done it right. Now, that answer on its own is worthless. As you've seen, we have to do a fair amount of work and kind of math to these equations in order to get them to match, and I want to see that work to help defend and back up this answer. Let me know if you can't figure it out, and I'll help you get there in class, but I need to see that done to get you your stamp. So, to help finish out this page, and this one has some little weird stuff going on, but it's not impossible. If we start by looking for the stuff we need, first thing I'm seeing here is 2H2 on the reactant side, and here I see 1H2 on the reactant side, so let's go ahead, multiply this whole reaction by 2, as well as our delta H value, which gives us negative 571.6 there, and that does give us our H2 ready to go. Next thing I'm going to look for is 2 carbon atoms on the reactant side still. I see 1 carbon atom on the reactant side, so I'm going to be multiplying the second reaction by 2 as well as its delta H, which gives us this. And our carbon is taken care of. Oh, that's where our check needs to go. Now, oxygen, as usual, is going to ruin everyone's day by being complicated. And so we're going to just leave that for right now. And then our C2H5OH here is definitely very clearly on the wrong side. So we're going to flip this first reaction, which will look a little bit like this, which gets me that C2H5OH that I wanted on the product side. Now I just need to remember to flip my delta H value. And now I can go back and check on that pesky O2. And since we are done looking at this version of this reaction, if we just zero in on the O2 molecules we have left, I have 2 O2 on the reactant side here, plus another 1 on the reactant side, gives us 3 total on the reactant side, and then 2 here on the product side. 3 minus 2, because they're on opposite sides, does give us the 1 O2 remaining on the reactant side that we're expecting. Or you can kind of visualize this as these 2 O2s and those 2 O2s canceling out to leave behind this 1 O2. So If that is truly all of our substances, then I can just add up these delta H values, and my overall delta H for that overall reaction is 1092.42 kilojoules. So, hopefully, amid all of this mess, you're finding a granule of sense and understanding, and so if you do, hopefully you can manage to work out some of the problems on this next page, page 3. And technically there's a couple problems at the top of the page and at the top of page 4 that you can answer from that information about energy basics that we went over at the beginning of this. But questions 3, 4, and 5 are Hess's law problems. So see if you can figure out how to multiply, divide, flip reactions there in order to get that big overall reaction. For each of them, I've got the answers posted so you can check your work, check your answers, and if you're not getting that answer, then we probably did something wrong. But I will help you in class next time if we're having issues here.